Hi, this is Sholey Physics. Today I'm doing an episode on centripetal acceleration and centripetal force. So we're finally down to a place where we need to consider something we haven't really talked about yet, that there's another way to change velocity besides changing the speed. See, velocity is a vector, remember that. So there are many situations, countless situations really, where objects move at a constant speed, but they change their direction. For example, a car going around a turn, um, planets orbit stars, uh, objects being spun around your head. Okay, you can get a lot of things moving at a constant speed. If you go to amusement parks, the bottom of a roller coaster hill is circular, like a circle, and you tend to go along that bottom at a constant speed, or just about. Maybe a little change in elevation, which causes a small change in speed. How about the Gravitron Rides? If you ever been on that one, it's occupants sit along the wall in the circular room, and the room starts spinning. And as the room spins faster and faster, the occupants feel like they're pressed against the wall there, and oftentimes the floor drops out or the wall slides up, and the occupants are still stuck by friction to the wall. So there's a constant spinning motion that's involved. And of course, as occupants, you feel a force. It feels like you're pressed into the wall. How about the bottom of that roller coaster? It feels like you're pressed down into your seat. How about around a turn in a car? It feels like you're pressed against the side of your car, against your door. So there's a force present even when the object that's moving in a circular motion is moving at a constant speed. There's this force present. So the acceleration that the occupants of the vehicle, of the rides, that acceleration that they feel is called a centripetal acceleration. It's due to a change in direction, not a change in speed. So we've really approached acceleration from a change in velocity over time, talking about an average acceleration here, delta v over delta t, and we've always been looking at the change, the amount of change. But what if a car is going on a turn at 60 miles per hour at a constant speed? Then it would seem like at a constant speed, let's say 60 miles per hour is the final and the initial is 60 miles per hour. It doesn't matter what the time is, let's say 2 seconds. This would still be an acceleration of 0. It's like there is no acceleration there. Well, this is around a turn, this would be called the tangential acceleration. And that is 0. That acceleration would be the rate, if this were a car going around a turn, that would be the acceleration in this direction. The tangential makes a tangent to the line. But so going around a turn at a constant speed would indicate that the tangential acceleration is 0. However, there's another component to acceleration in a turn, and that is the radial acceleration, and that's also what we're going to call the centripetal acceleration. Centripetal. And that is not 0 in a turn, even when the speed is constant. So this centripetal acceleration or radial acceleration is in this direction. And this is the one we're going to talk about. What is that radial acceleration? What does it come from? And how do we get it from a turn? I'm going to delete some of this that I just drew on there. There we go. And a little bit of that. Okay. All right, now, just to set up the scenario, I just gave you a very common situation that many of you may be familiar with. Let's take a car that's starting to enter a turn. And what I'm doing is I'm drawing a partial turn, a roadway here, where the car might be taking a turn with a circular kind of motion. You don't always have to move in a circle to have a circular motion. It could be a semicircle or part of a circle, a curve. The car takes a curve. So as the car is driving along, it might start out with a velocity this way. There is no centripetal acceleration at this moment. But when that car goes into the turn, there's a force that it relies on, friction, to keep it in the turn. See, its tendency is to, objects in motion tend to stay in motion. It's going to be to drive off the road. But as long as there's no ice on the road, it's not slick, then this car will begin to turn. And later on, it'll be moving in this direction. Okay, so it'll be moving in this direction. At this moment, just follow the red lines. It's moving at in that direction. So it starts out going up, and then it's sort of northeast, northeast, and then it's more of a east-northeast kind of direction a moment later. And it's making this turn. And all the while, this car relies on friction, pulling it in towards the center of the turn. And I'm going to come back to that, the force aspect, later on in this presentation. But this is the picture here. We've got an object in a turn, and where is this centripetal acceleration coming from? I'm going to back it up, take away our imaginings here, imagined turn. All right. So the car at this moment, at point 1, has a velocity in this direction. And we're going to compare it to a moment later when it's got a velocity in this direction. Of course, the velocity is given with the sizes and such. Now, when it makes that turn, several things are changing. First, it's changing position in the X and Y direction. It's going more in the Y direction, let's say to the north, and it's also going to the right direction, you could say to the east. So its change in position goes from point 1 to point 2. Its change in position I'm labeling delta x. That's what that is right there, okay? Now as it goes around the turn, the actual path it takes is delta s. That's the arc length of the circle, delta s, that's the arc length. All right, so that s value is, on this diagram, it's a little bit longer than delta x because it's not following a direct route. And we'll come back to that too. What else you see here is labeled the radius. You'll notice the distance from the center of the turn is the same at point 1 as it is for point 2. So the letter R labels the radius of that turn. All right, so what else do we have labeled here? Finally, we've got V1, and V2. This is the velocity at each point. And I will say here, we're assuming that the magnitude of V1 equals the magnitude of V2, meaning we're moving at a constant speed. But this car, this object, whatever it is, it could be a bucket on a string or a rope you're swinging around your head. Don't let the water splash you. That speed is staying constant as we're changing direction. But as you see, V1 and V2, the difference is their directions. So if we compare those two, I'm going to grab these. Here's V1 and here's V2. It's keeping the size and the direction of each of those vectors. If I compare them, well, first off, I did make a claim here that they're the same size, so I'm going to use the ruler to measure each of these vectors just to ensure. So that one's about 43 units long there. I guess it's supposed to be centimeters. And if we tilt this upward, we should be able to get, look at that, about 43 long there. Okay, so they're both about 43 centimeters long. I'm going to put that tool away. All right, so this is V1 and V2. So what has changed between position 1 and position 2 is the direction. So we might say the change in velocity is from V1 to V2. That's the direction of the change in velocity. And how much is that V? How much is that change in V? When we place it on that circle, and you'll notice it cuts the position between 1 and 2 exactly in half. The change in V is the change of velocity between 1 and 2. If we cut that in half, look where it points, directly at the center of the circle. So this acceleration, whatever it's going to be, our delta V, is going to be pointing towards the center of the circle. There's a direction to this acceleration. It is a radial acceleration. Now, if I keep that triangle there and I compare it to the other triangle right here, right? You'll notice something with your eyeball. You might notice that these are similar triangles. Similar meaning they have the same exact angles, but different sides, different lengths of the sides. So if I rotate this a little bit, you're going to see the similarity really come out here. Just rotate a little bit more. And there we go. So you can see that they have exactly the same angles, just different sides. Now this is important because if we compare these sides, we get ratios coming out. And this is going to be what's useful. There's a ratio between the sides of this triangle, and we'll call this is delta x right here. And we've got this triangle over here. This is side V1, and this side is V2. And this side is delta V. What we may do next is now compare the sides. Because these are similar triangles, we can compare a couple of ratios of the different side lengths of these two triangles, and they're going to be exactly proportional. So if we compare like delta V to delta X and V1 to R, then we can start up with a ratio. Delta V, this side, is to V1, this side, as delta X over there is to the radius R. All right, now we're trying to get it back to what is a radial acceleration. So the delta V, the change in velocity between V1 and V2, is labeled here. But if we solve for delta V with these ratios, we're going to get a V1 pops up here over R times delta X. All right, so that's delta V equals V1 over R delta X. But an acceleration, and this is going to be the radial acceleration or the centripetal acceleration, is a delta V divided by delta T. So of course would be the average acceleration. Do you notice how the delta X is in the direction exactly toward the center, that radius of the circle at this midpoint here? This is showing you it's an average acceleration, okay? So this average radial acceleration would be this quantity up here, delta V over delta T, which would be V1 over R times delta X over delta T. Now, what is this creature here, delta X over delta T? That's like an average velocity between point 1 and point 2. And as T approaches a smaller and smaller number, as T approaches 0, what is delta X going to look like? Well, delta X is going to become delta S, and just as on a XT graph, let's pull out some Unit 1 stuff. If we had a position time graph, and there might have been some changes in position, if we look at, like, let's say that a large change of position, a delta X over delta T, there might be some different kind of instantaneous velocities within there. But if we start bringing that delta T into a smaller and smaller view, there's going to be a much smaller and smaller delta X. And so that that point is approaching the slope of that XT graph, which is the instantaneous velocity. So as we bring this change in T less and less and less, lower and lower and lower, we're talking about a small change in position. If you consider that car going around the turn, instead of making a big section of swath of a turn, let's consider just a small little swath there. That would correspond to a small delta T or dt. And this little change over here will be little dx. And that ratio will be the same as this one. So as t approaches 0, what it comes down to is this approaches dx dt, which is an instantaneous velocity as well. So all in all, what this is saying is that whatever v1 was, if we consider that magnitude, we've got another magnitude of velocity here. We end up with a v times v divided by r, a v squared divided by r. If you recall that the magnitudes of the velocity, v1 and v2, are the same because it's a constant velocity, then delta x over delta t is the same as v1. So we end up with a ratio that's turns into a v1 squared over r. V squared over r. In its most generic form, an object moving at a constant speed around a turn experiences a centripetal acceleration or a radial acceleration of v squared divided by r. And that's all you really have to take away from all this is v squared over r is centripetal acceleration. It gives us a magnitude of an acceleration that changes the direction of an object. Not the speed, but the direction. All right. So where can we take that? Situation number 1. We've got a mass on the end of a string, a tension string. And there's a tension as this mass is spun. Okay, it's spinning around and around and around. Now let's use a little bit of circular motion here. Let's bring that out. I'll go ahead and grab a circle, make a circular kind of motion. Let's unfill that. All right, circular kind of motion. Move that over a little bit. There we go. Looks like my circle is not quite big enough. There we go. So you get the sense of a circle there. So there's a tension force that's pulling it in. There's going to be a radius, a turn radius, okay? And this mass at this moment is moving with a velocity v out this way. Now I'll give it some numbers later on, and we'll see how this works. So you got a velocity v. Keep in mind a little bit later on, it's going to be here. And which way is it going to be moving? In this direction with the same amount of velocity v. All right, but what is that velocity? Let's, like I said, let's get a little bit of circular motion information going on here. There's a quantity called period, which is the time it takes for one cycle. This is the period. So you might be in first period or second period or third period in your school. And a period is always a set time long. It could be a 50-minute period. You might be a 90-minute block time. That's still a period. All right, first period is, let's say, 50 minutes long. Second period is 50 minutes long, and so on. It's a periodic kind of a repeating motion that you go through. I go to first block, second block, third block, and so on. And they're all the same amount of time. Now, when you're spinning objects, it takes a certain amount of time to go around that circle. So if, let's say the period for the spin is a half second, then how can we figure out the velocity of that object? Well, let's say we're going to need a radius for this. Let's give a spinning radius of 0.75 meters is a spinning radius for this mass on the end of a tension string. And so the big question is, what is the velocity then? I'm just using a little bit of geometry. That is not a circle. That is not a circle either, but it's a better circle. If our radius is 0.75, and it takes a half second to go all the way around this thing, then what is that velocity? Well, it's a constant speed, so we could use the average speed would be equal to the average would be equal to that constant speed. So average velocity, you might recall, is just a dx over dt. Now in this case, it's an arc length. It's a distance around a circle. So there's a slightly different letter we use here is just an s. And if you recall from geometry, the arc length around an entire circle is 2 pi r. R times the angle in radians. So 2 pi radians times r is the arc length. So if we wanted a velocity out of this, we'd take a 2 pi times the r divided by the time period for one cycle. So 2 pi r is one cycle around, and the period t is the time period for one cycle. And it would just be a matter of plugging in those values, an r of 0.75 and a time of a half second. So let me rewrite that over here. It's not really clear there. 2 pi times 0.75 meters divided by a half second. Now 2 divided by a half is 4, so in essence we'd have a 4 pi times 0.75, and 0.75 is 3/4, so 4 times 3/4 is 12/4, or about 3 pi, and that would be in meters per second, 3 pi meters per second. You can of course multiply that out. It's going to be somewhere around 10. 3 times 3.14 is just a little less than 10 meters per second. So we'll just say it's about 10 meters per second in speed. All right, so that's a way to figure out a speed, a velocity from it. All right, so my question might then be is, well, this is awkward because t is period, and that's what I was calling it over here in a sort of different discussion. Is this t over here the same as that t? That's why you come to Shirley Physics, because I do the messing up for you. That way you learn from it. Don't get these two confused. This t over here is referring to a tension force. So I'm going to be better about this. I'm going to relabel this one over here. Let's call that Ft, the force of tension. There we go. And it's not the period force either. It's just the tension force. And this is an object being spun horizontally. So what do we do with that? Let's make a force diagram. How much is that tension force going to be? What is the tension in that string going to be? And this is a pretty good thing to study if you're ever deciding what kind of cable to use in your own spinning applications. Okay, you want one that's going to hold the mass on the end. You ever seen the very, very, very original Batman movie? The Batmobile goes around a corner running away from Joker and Joker's minions, actually, and he shoots this cable out, and it grabs onto this like steel girder on the road, and it helps the Batmobile to go around its turn, going super fast, like 35 miles per hour. But that's pretty good for a 90-degree turn on a local street in the city. But meanwhile, Joker's goons can't make that turn, and they just go spinning off. You know, not enough centripetal force there. So in this kind of scenario, if we're looking from the top, we got normal force going up and the weight going down. Those two forces are balanced and they'll cancel. The only net force is this tension force. And I'll just keep it the same direction. But I'm going to call that direction positive. How about that? That's the direction of the force toward the center of the turn. So that's also the direction of the acceleration. All right, pretty easy. So we're going to, next, there's no other forces acting here. Sum of the forces equals mass times acceleration, Newton's second law. And this is simply where centripetal acceleration comes in. Everything else is the same. We're still drawing a force diagram. We're resolving any angles we need to do first. Occasionally going to need to do that with circular motion, but in this case not. There's only a tension force. That's the only net force causing a turn here. So tension is the only net force. You take the mass of the object and the acceleration. What is that? Oh, the acceleration 0 because the velocity is not changing. Wait a second. There is a radial acceleration, this centripetal acceleration. So I'm going to call it AC, the centripetal acceleration. Let's remember to use that. How much is the tension going to be then? It's going to be m times, what is AC again? Let's go back. Oh yeah, that radial acceleration, that centripetal acceleration is v squared over r. I've got that info. So we're just going to substitute v squared over r, and that is all you're doing that's different from before. Different from before, referring to like work with friction and other things like that. Here's my ruler, I'm going to get rid of it. So we're just, at this point, if you can identify, hey, this is a force that's causing a turn, causing a change in direction, then you set all those forces that cause a change in direction, in this case is only tension, set it equal to mv squared over r, and that's it. So we could figure out a tension here. Looks like we're going to need a mass. I'll call this a 2 kilogram mass. The velocity we determined was 3 pi. And we're going to have to square both of those, okay? But so 3 pi quantity squared divided by the radius. The turning radius is 0.75. So r comes back into it there. And of course, we can get an, I'm going to use my approximation of 10 meters per second here. So 2 times 100, that's 10 times 10, divided by 3/4. And that's equal to 2 times 100 times 4/3. Dividing by 3/4 is like multiplying by 4/3. And we get approximate tension force here. 200 times 4 is 800, and 800 divided by 3 is about 267 newtons. How about that for mental math? Oh yeah. Okay. So that's scenario number 1. All right, scenario number 2. Guess what? It looks the same. Looks like the same kind of thing. Let's do a car around a turn. All right. What is the mu? Static mu required. Okay, so what's the degree of grip? To get a 1,000 kilogram car to go around a turn of radius, let's call that radius, the turn radius, 500 meters at a velocity of, here's my car. It's going to go around turn at a velocity of, let's go 25 meters per second. Write it twice there. Okay. What's the mu required to make this happen? Now, this of course would be the mu for the maximum amount of friction. So any faster than 25, or if we change around the radius or something like that, if we tighten the radius a little bit, then this car is going to overcome that static friction and start squealing and sliding off the road. The wheels will start squealing. So we're dealing with some maximum static friction. And if you might recall, static friction is less than or equal to mu s times normal force. And that's where mu is going to come into this. We're going to have to get friction involved. But in this particular case, we need a maximum friction. So that's where friction is equal to, okay, equal to mu times normal force. All right, here's our mass, here's our car. It's going around a turn. The weight is equal to the normal force. Oh, I guess we should put that in there. I'll go ahead and make this let's look from behind the car. As the car is turning to the right, there's some normal force up. There's the weight down. And we can go ahead and solve that. Solve for that weight. 1,000 times 9.8 equals 9,800 newtons. Excellent. Now I get the normal force up. All right, is that it? Well, let's make it a right-hand turn. So there's going to be an acceleration toward the right due to a force. Now, what force is causing this car to turn to the right? Without this force, this car would go straight and go straight off the road and not be able to turn. So what is this magical force? Friction. Static friction between the tires and the road. That's what allows it to turn. It's friction that is the centripetal force in this scenario. And that's what you should ask yourself. Oh, here's a scenario with something turning. What is the centripetal force? What force causes this thing to change direction? In this case, it's friction. All right, so let's sum the forces. I've got no angled forces here to resolve. Set them equal to ma. And the x direction, all right, we're just looking at these x direction forces. There is only static friction. Now you might be saying to yourself at a moment here, hold on a second, how is static friction causing us to accelerate? Well, just recall that it takes grip between the tires and the road to make the car turn. But friction is causing a change in direction, not a change in speed. So this is not a speed up, this is not a slow down kind of kinetic friction. This is stuck to the road, but gripping kind of friction. Without this grip, the car wouldn't stick to the road. And as the car tries to move in this direction, keep in mind is the friction has to pull in towards the center of that turn to make it happen. So this is static friction. It's not causing a change in speed, but it is causing a change in direction. So this acceleration over here has to be a v squared over r. There it is again. Once we identify the direction where there's a change, the x or y direction, which one is causing the centripetal acceleration, we're going to set that a equal to v squared over r. Now let's bring out the mu. Substitute for friction, static friction there. Mu times normal force is equal to mv squared over r. Let's take a little catalog of what we've got so far. I've got the velocity, I've got the mass, and I've got the radius of the turn. So all these are taken care of. Our target is mu s. So what's the only other thing we need? That's the normal force. If we sum the forces in the y direction, that's where the normal force is. We see normal force minus the weight is equal to mass times v squared over r. No, it's not turning in the y direction. It's at rest in the y direction. Normal force is balanced by the weight, so that y acceleration is 0. So what's this mean? Normal force is equal to the weight. Excellent. We're ready to go. Mu s times the weight, which is the normal force, equals mass times velocity squared divided by the radius of 500. All right. Actually, let me go ahead and take that, just divide both sides by 1,000 here. That'll give us a 9.8. Hey, acceleration due to gravity. How about that? Divide 1,000 out. 25 squared is 625 divided by 500. And my mental math isn't that good. But if we're taking 625 divided by 500, that's about that's the same as 1,300 over, 1,250 over 1,000. That's the same ratio there. And dividing it by 10, sorry, that should be 1,000. And dividing this by 10 would make it about a 10,000. So divided by 9.8 would give us approximately another 0 down there. So my mu-s value is approximately equal to 1,250 over 10,000, which is divided by 10, 100, 1,000, 10,000, about 0.125. It's a little bit, we're really dividing it, we had a 9.8 here, so it's going to be a little bit more than that. So I'll just say about 1.13 is the static mu required to make that happen. All right, all that bumbling there at the end is just some math you can do on your calculator. All right, so the setup is the same. Draw a force diagram, identify the force in the direction that it has the centripetal acceleration, set that force equal to mv squared over r, plug in your knowns and solve for your unknown. On this page, same kind of thing, force diagram, identify the direction that has the centripetal acceleration, that sum of the forces equals mv squared over r, plug in your knowns, solve for your unknown. It's the same exact situation. This is all we're adding to it from our last few lessons on friction and drag. That's the only thing we're adding here. All right. Now I'm just going to intro this next one just to consider, and it'll be your job in the next couple days to explore several different situations, many different situations involving centripetal force. These are just some. But consider the banked turn. All right. the banked turn. If you look at a car turn from behind on a banked road, what helps it turn? Well, gravity doesn't, but normal force does. You see, normal force is going to have a component that goes into the turn. And if we're looking behind, okay, imagine a turn here going to the left. And this is the slope of the road. Here's the lines as the road turns ahead. Okay, we're looking from behind. What's going to be the tendency of this car? How's it going to tend to move? It's going to tend to keep going straight off the road. All right, but the normal force is giving a little bit of a component to the left. But what else is? Friction. So friction would tend to go this way. You see, if the car is going to tend to go up the slope and off the road, then there has to be a friction. Friction is parallel to the road. So it's either going to be to the right or the left. But this friction is going to be keeping it in the turn, keeping it from moving there, so from sliding up the turn. So my question here might be, what is the maximum velocity that this sucker can take around a turn, where mu s is about 0.7, and that's sort of standard for some road conditions and tires. 0.7 is a decent static mu. So what's the maximum velocity this car could take around this particular turn? I notice I didn't give you a mass value. I'm going to leave that out. So here's mg. There's our weight. Friction, that's mu s times normal force, and the maximum velocity would correspond to a maximum static friction, where static friction is equal to mu s times normal force. It's not less than. All right, we could of course go a little slower and you'll be fine. So in this kind of scenario, it brings together a few different pieces. First off, you might be thinking, oh, object on a slope. That means after I do my force diagram, I'm going to need to rotate my view. Well, in this case, no. You see, what we want to do is keep this car at the same height, at the same altitude around this banked turn. We don't want it sliding down the slope. We don't want it sliding up. So its y direction acceleration is 0 in this scenario. We don't want it to go up the slope and crash into a wall up here, and we don't want to turn too much and go off the road down there. We want to go just follow a path down the middle of the road. So the y direction acceleration is 0. When we draw our force diagram, more clear of all this other stuff, friction has an angle theta. Okay, as you can see there's the angle theta. And with a bisecting line and two parallel lines there, this angle is going to be equal to that angle. All right, so there's our angle theta and our friction. Normal force is up kind of this way at a weird angle. And again, so this looks like sort of a big angle here. If this slope is up from the horizontal in angle theta, the normal force is over from the vertical in angle theta. That's why I'm going to fill in on my diagram here. So there's the angle theta also. And there's also the mg, the weight pulling down. So this is actually the force diagram we need to use here, because in addition to the acceleration in the y direction being 0, there is a acceleration in the x direction. And what is that? It is the centripetal acceleration. Now this is not a force, but the left-hand turn is what we're trying to make. This is going to be a left-hand centripetal acceleration. So we want to preserve that aspect. We want our sum of the forces in the x direction to include the direction of the centripetal acceleration. So my next step, I'm going to resolve these angled forces into their components. mg is down. We've got the normal force going up and to the left. So up and to the left. The up component is going to be Fn. We don't know what that is yet. Fn cosine theta. It's adjacent to the angle reference. So it's a cosine. That makes this component Fn sine theta. And friction. You might have noticed I made this component larger than the weight. And I did that on purpose because if you look at the friction, it's actually pulling down a little bit as well as to the left. There's a downward component of friction and a left-hand component of friction. The left-hand component is adjacent to the angle theta, so that's going to be force of friction cosine theta, and that makes the downward component force of friction sine theta. And that's actually our force diagram that we need to work with before we jump into Newton's second law. All right. Now, there's friction involved, so I will say we will need the normal force component. We do need to compare that to mg. So let's go ahead and do the standard sum of the forces in the y direction equals may. There's normal force cosine theta up, and down we've got force of friction sine theta and a negative mg. All right, so the normal force component is going to be related to the weight and that little bit of friction going downward. And what about A? Remember in the y direction, we're not going to be sliding up the slope or go down the slope. So the A direction, the y direction acceleration is 0. It's not going up or down the slope, so it's vertically at rest. Now we've got a friction in here and a normal force, so it'd be appropriate here to substitute normal force for mu static times normal force. Sorry, substitute friction for mu static times normal force. And we've got a 0 on this side. I'm going to add mg to both sides, make that equals mg. We can now factor out the normal force Fn, and we'll have in there a cosine theta minus mu s sine theta equals mg. So out of all this ugliness, it's here. It's not hard to get, but it's an ugly algebraic maneuver here. We're going to have an mg divided by the quantity cos theta minus mu s sine theta. There's the normal force. Not very conventional, but that's what it is in this scenario. That's why I'm working it out for you. This is one of the tougher ones to work with in centripetal motion, centripetal acceleration. All right, now let's look at the x direction, because that's more interesting here. That's really what we're trying to focus on. Our target variable is a maximum velocity, and if you've been following the flow here, this velocity around the turn is going to be related to this centripetal acceleration. The reason I'm circling the x direction is because these two forces pull the car to the left, a component of the friction and a component of the normal force. The banked road is what helps out the turn. That's why especially NASCAR tracks and race car tracks are banked in the turn. It allows them to make that turn at a higher speed because the normal force of that turn adds to the centripetal acceleration. It helps the vehicles change their velocity more quickly by changing the direction. So in the x direction, there are only two forces, or two force components, Fn sine theta plus force of friction cosine theta. You see they're helping one another. And the acceleration isn't going to be 0. It's going to be the v squared over r. See what you do, the centripetal forces, you decide which way the direction of the centripetal acceleration is it in. This is a left-hand turn. We don't want to go up. We don't want to go down the bank. We want to go directly to the left. So when you draw out your force diagram, which forces are going to the left? These two. So together, they're adding, they're summing to produce that centripetal acceleration. Now let's sub in what we know. We've got an Fn sine theta plus substitute in mu s times normal force cosine theta equals mv squared over r. All right, we are looking for that V max. So this is going to be our target. Let's not lose sight of that. And oh, here we can again factor out a normal force. And it continues to be quite ugly because we now need to substitute normal force back in here. So we're going to substitute that in on this side. But as you see, we're going to get a multiple of mg. We're going to have an mg. I'll keep that out in the front. And up in the numerator will be this piece, sine theta plus mu s cosine theta, divided by, this is going to be in the denominator, cosine theta minus mu s sine theta equals mv squared over r. Excellent. The masses cancel. That's about all that cancels there, though, unfortunately. And so as long as we know the r of the turn radius, and the angle of the turn, we can figure out the velocity. Multiplying all this out, I get a velocity. We'll go ahead and solve for the velocity here. So what does v equal? It's going to be g times big R times all this junk. Yes, I'm going to go ahead and write it out. You may be able to simplify that a bit, but I'm not going to spend time doing it. That's a plus on top. Don't want to get that mixed up. And a minus on the bottom. And because we're going for v, we would have to take the square root of both sides. So square root of v squared is v. It's on the left. That means we're going to take a square root of all that. And there it is. What is the v max? We can plug in a mu. We can plug in an angle. And we would also need to plug in a turn radius. Those all would affect the v. But once you do that, you got your solution. All right, so that was a banked turn. That's probably the most complicated, kind of, mathematically complicated and force diagram wise complicated scenario you're going to have. But what else could be in a turn? You could have a planet under the influence of Newton's gravitation law. If you haven't learned that yet, it's gm1 m2 over r squared. That will be coming up in this course if you haven't gotten to it yet. And for my class, it'll be later in this unit. So just, I think it's our next lesson. We'll introduce that universal gravitation law and get some centripetal force in there as well. You might have a normal, I talked about that Gravitron ride. So you might have some scenarios, if you're a mass stuck up against a wall, and this wall is part of a room that's spinning. There's a little radius here. All right, then the normal force is pushing you out from the wall. There's going to be some friction holding you up on the wall and weight pulling down. So in this kind of weird situation, the normal force pushes out horizontally, and that's going to be equal to the mv squared over r. There's one cool scenario with normal force being the centripetal force. There's been some space station concepts. How do we get people living in outer space for a long period of time without losing a whole lot of bone density? It's important to have that weight feeling and to hold up your bone structure and to keep your bones healthy. So what's been conceptualized is for long-term space station living is living in this section of a station that actually turns and spins, and people would be standing with their feet against the floor that spins. It's actually the wall that spins, if you want to think about it like that, as it rotates. So that's a very similar kind of situation. The apparent force is the normal force they would be feeling is equal to mv squared over r. You got cars around turns. You've gone over that. You got spinning things on strings. So these are some common scenarios you're gonna find. But all in all, remember when you get something equals ma in the direction of the centripetal acceleration, all you're really doing here, the takeaway from all this, is substituting a v squared over r, and let the Newton's second law do all the talking after that. That's all I have to say about that.